You are standing on a layer of rock so thin that if the Earth were scaled to the size of an apple, you would not be able to see it with the naked eye. Everything you know, cities, mountains, ocean floors, the deepest mines ever drilled, exists within a film so delicate it would peel away like skin. Beneath it lies almost everything. The engines of tectonics, the recycling of continents, the remnants of worlds that collided before there was breath or bone. None of it can be touched. None of it can be seen, and yet it has been turning, shifting, convecting for longer than multicellular life has existed, supporting a surface we mistake for permanence. The crust is all you have ever known. It is the only solid ground any human being has ever walked on, built upon, or broken into. The deepest hole ever drilled, a Soviet experiment on the Kola Peninsula that took decades to complete, reached just over 12 kilometers down. At that depth, the rock was hot enough to soften drill bits, and the project was abandoned not because funding ended, but because the Earth resisted further. 12 kilometers is less than the distance some people drive to work. It is a scratch. The continental crust beneath your feet averages about 35 kilometers thick, though in some mountain ranges it swells to 70. Beneath the oceans, where the crust is younger and denser, it thins to as little as 5 or 6 kilometers. These are not vast distances. If you could walk vertically downward at a steady pace, you would pass through the entire thickness of oceanic crust in under an hour. And yet, no human has ever touched the base of it. No machine has ever returned from the boundary where crust meets mantle. Everything you think of as deep, the Mariana Trench, the mines of South Africa, the subterranean lakes discovered kilometers below ice, is shallow. It is surface. The crust is not a single thing. It is a patchwork, a mosaic of plates that drift and collide and pull apart at speeds slower than fingernails grow. Some of the rock beneath you is older than complex life. Some of it formed when dinosaurs walked above it. Some of it is so young it has not yet cooled fully from the heat of its creation. Granite, basalt, limestone, sandstone, these are the materials of accessibility, the substances that can be held, tested, dated, and understood. Geologists have spent centuries mapping the crust, tracing its faults and folds, reading its history in the layers of sediment and the angles of ancient collisions. It is the only part of the planet that can be studied directly. Everything else is inference. Everything else is educated guessing built from seismic waves and mathematical models and the behavior of materials under pressures no laboratory can sustain for long. The crust is the known world. What lies beneath it is not. To understand the scale of what you are standing on, you must first understand what you are not standing on. The Earth is not a solid ball of rock with a thin coating of air and water. It is a layered sphere, and the layers do not exist in equal proportion. If you were to slice the planet in half and look at it edge-on, the crust would be barely visible, a line so thin it might be mistaken for the edge of the image itself. The mantle below it would dominate the view, a vast region of rock that makes up 84% of the Earth's volume. Beneath that, compressed into the center, the core, a sphere of iron and nickel so hot it glows, though no light escapes it. The crust, for all its mountains and valleys and the weight of its oceans, is an afterthought. It is the skin on cooling soup. It is not structural, it is not foundational, it is simply what cooled first. And yet, it is everything to you. The minerals that build your bones were drawn from it. The carbon in your cells cycled through it. The water you drink fell as rain and filtered down through its pores before rising again in springs. The air you breathe was exhaled by ancient volcanoes that punctured it. Every resource, every element that sustains life came from this thin, fractured shell. You are made of crust. You live on crust. You have never left it. The entire history of human civilization, every empire and city and field and road, exists within a zone so thin that if the Earth were reduced to the size of a basketball, you could not detect it with your fingertips. And beneath that zone, supporting it, driving it, reshaping it over spans of time too long to feel urgent, is almost everything else. The mantle begins where the crust ends. The boundary is called the Mohorovičić discontinuity, named after the Croatian seismologist, who discovered it in 1909 by studying how earthquake waves changed speed as they passed through the Earth. It is not a sharp line. It is a transition, a place where the chemistry of rock shifts, where minerals rearrange under pressure into denser configurations. On the human scale, it might as well be a wall. No tunnel will ever reach it. No probe will ever sample it directly under the continents. It is farther away than the International Space Station and vastly harder to reach. You are closer to the edge of space than you are to the bottom of the ground. The mantle is not empty space. It is not liquid in any sense you would recognize. It is rock, solid rock, but rock under such pressure and heat that it behaves over geological time like a fluid. If you could somehow stand at the boundary between crust and mantle, you would not see a glowing sea of magma. You would see stone. Dark, dense stone, rich in iron and magnesium, compressed by the weight of everything above it. The temperature there hovers around 500 degrees Celsius, hot enough to melt lead, but not hot enough to melt the rock itself under that pressure. The mantle does not melt. It creeps. It flows the way glaciers flow, the way glass in old windows is said to flow, though over spans of time so long that the movement is invisible on any human scale, a few centimeters per year. The speed at which continents drift, the speed at which mountains rise and oceans close. The upper mantle extends from the base of the crust down to a depth of about 410 kilometers. That is deeper than the distance from London to Edinburgh, deeper than the length of Japan. If you could descend into it at a constant rate, it would take you days of falling to reach the bottom, and yet it represents only a fraction of the mantle's total thickness. The mantle continues downward for another 2,500 kilometers, making up the bulk of the Earth's interior. It is not uniform. It is not static. It is divided into regions where the minerals that compose it change phase under pressure, rearranging their atomic structures into forms that cannot exist at the surface. Olivine becomes wadsleyite. Wadsleyite becomes ringwoodite. These are not different substances. They are the same elements, silicon, oxygen, magnesium, iron, locked into different crystal lattices by forces you cannot reproduce in any laboratory on Earth without sophisticated equipment. The deeper you go, the stranger the rock becomes, not because it is made of rare materials, but because the conditions transform common ones into configurations that only exist in the deep. We know the mantle exists because of earthquakes. When the ground ruptures along a fault line, it sends waves radiating outward in all directions, waves that travel through the Earth as well as across its surface. Some of these waves are compressional, pushing and pulling the rock in the direction they travel. Others are shear waves, twisting the rock perpendicular to their path. Seismologists have placed instruments all over the world to record these waves, and by measuring how long they take to arrive, how their speed changes, and where they refract or reflect, it is possible to build a picture of the planet's interior. It is the same principle used in medical ultrasounds, but on a planetary scale. The Earth has been scanned, layer by layer, not with light or sound in the ordinary sense, but with the energy released by its own instability. Every earthquake is a probe. Every tremor is data. Over more than a century, those data points have accumulated into a map of the unseen, a model of what lies beneath, accurate enough to predict the behavior of seismic waves through regions no human will ever visit. The mantle is not homogeneous. It contains plumes of hotter material rising from deep within, columns of rock heated by the decay of radioactive isotopes that have been disintegrating since the planet formed. These plumes move slowly, sometimes pooling beneath the crust for millions of years, before breaking through in bursts of volcanism that resurface entire regions. Iceland sits atop one. Hawaii is the surface expression of another. Yellowstone, with its geysers and calderas, marks a plume that has burned a track across North America as the continent drifted over it. These are not isolated phenomena. They are evidence of convection, the transfer of heat from the deep interior to the surface, a process that has been ongoing for more than 4 billion years. The mantle churns. It rises in some places and sinks in others, dragging the crust along with it, pulling continents apart, driving them together, recycling ocean floors back into the depths where they melt and are eventually returned in different forms. This is the engine that powers plate tectonics, and it operates entirely out of sight. The rock in the mantle has never seen sunlight. It formed in darkness and pressure, and it will remain there for as long as the Earth exists. Some of it may have been cycled to the surface in the distant past, erupted as lava and then subducted again, pulled down by the sinking of an oceanic plate. Some of it has been isolated for billions of years, never mixing with the material above or below it. Geochemists can sometimes detect traces of this ancient rock in volcanic eruptions, isotopic signatures that suggest the mantle is not a well-stirred soup, but a layered, partially isolated system with regions that have remained distinct since the planet's formation. There are parts of the Earth's interior older than the oldest surface rocks, preserved not by luck but by depth, by the sheer weight of everything pressing down on them, preventing their return. To descend through the mantle is to pass through a gradient of increasing pressure and temperature, a transition so gradual that no single boundary defines it, yet so extreme that the rock at the bottom is nothing like the rock at the top. The upper mantle is relatively cool, relatively accessible in the sense that we can infer its behavior from volcanic rocks and seismic data. The lower mantle, beginning at a depth of about 660 kilometers, is something else entirely. It is hotter, denser, less understood. The pressures there are measured in hundreds of thousands of atmospheres. The temperatures exceed 2,000 degrees Celsius. If you could somehow place a diamond at that depth, it would not scratch the surrounding rock. It would change phase, rearrange its atoms, become something else under the force of the planet, pressing inward on all sides. Nothing survives the deep unchanged. The lower mantle is a place defined by stillness and weight. It begins at a depth of roughly 660 kilometers, where the mineral structure of the rock undergoes another transformation, and it extends downward for nearly 2,000 kilometers more, occupying more volume than any other layer of the planet. If you could extract the lower mantle and set it beside the rest of the Earth, it would outweigh the crust, the upper mantle, and the outer core combined. It is the largest single region of the planet, and it is almost entirely unknown in any direct sense. No sample has ever been taken from it. No instrument has ever measured its composition in situ. Everything we think we know about the lower mantle comes from indirect observation. Seismic waves that travel through it, laboratory experiments that attempt to recreate its conditions, and computer simulations that model how rock behaves under pressures that exceed 1,000,000 times the atmospheric pressure at sea level. It is a place constructed from inference, a scientific ghost made real through mathematics. The rock there is no longer olivine or pyroxene, the minerals familiar from surface geology. It has transformed under the crushing force of depth into a structure called bridgemanite, a magnesium iron silicate that exists nowhere on Earth's surface because it cannot remain stable at low pressure. If you could somehow bring a piece of the lower mantle to the surface, it would not survive the journey. It would decompose, rearrange, lose the structure that made it what it was. Bridgemanite is the most abundant mineral on the planet, and no human being has ever held it. It makes up nearly 40% of the Earth by volume, and it exists only in a realm we cannot reach. The irony is quiet but absolute. The substance that dominates the planet is inaccessible, present in quantities vast beyond comprehension, yet absent from human experience. The temperature in the lower mantle rises with depth from around 2,000 degrees Celsius near the top to perhaps 4,000 degrees near the boundary with the core. These are not the temperatures of fire or molten lava. They are hotter. They are the temperatures of planetary formation, the residual heat from collisions that happened more than 4 billion years ago, combined with the slow, steady decay of uranium, thorium, and potassium buried in the rock. The Earth is still cooling. It has been cooling since it formed, radiating heat into space at a rate imperceptible on human timescales, but relentless over billions of years. The lower mantle is part of that cooling process, a thermal reservoir that transfers energy upward through convection, gradually losing the heat it inherited from the solar system's violent youth. One day, far in the future, the mantle will cool enough that convection slows and then stops. The surface will freeze. The magnetic field will fade. But that day is billions of years away, and for now the deep remains hot active and utterly indifferent to the life clinging to the crust above. The lower mantle does not flow like the upper mantle. The pressures are too great, the viscosity too high. It creeps even more slowly on timescales measured not in millions, but in hundreds of millions of years. And yet it is not static. Tomographic images constructed from seismic data reveal structures within it, regions where the rock is slightly denser or slightly hotter than its surroundings, variations that suggest the mantle is not a uniform blanket, but a textured, dynamic system. Some of these structures appear to be the remnants of subducted oceanic plates, slabs of crust, that were pulled down into the mantle by tectonic forces and now rest at depths of 1,500 or 2,000 kilometers, slowly sinking, slowly heating, slowly blending back into the rock around them. Others may be the roots of mantle plumes, columns of hotter material rising from the boundary with the core. The details are unclear. The resolution of seismic tomography is limited. But the implication is undeniable. The mantle remembers. It holds within it the history of the surface, the record of continents that collided and split and collided again, written in the density and temperature of rock buried far beyond retrieval. To think of the lower mantle as separate from the rest of the Earth is a convenience, not a reality. It is connected to everything above and below it. Heat flows through it. Material moves through it, though so slowly that no single feature remains fixed for long on geological timescales. It interacts with the core at its base, with the upper mantle at its ceiling, and indirectly with the crust through the convection currents that drive plate tectonics. It is part of a system, a machine of pressure and heat and motion that has been operating since the planet was young. And yet, from the surface, it is invisible. You cannot feel it. You cannot detect it without specialized equipment. If every human being vanished tomorrow, the lower mantle would continue exactly as it has, unaffected and unaware, churning and creeping and transferring heat in patterns that will persist long after the sun begins to die. There is something humbling in that. Not the humility of smallness, though you are small, but the humility of irrelevance. The processes occurring in the lower mantle are not for you. They do not serve any purpose you can name. They are not hostile, but neither are they benign. They simply are, continuing because the laws of physics dictate that heat flows from hot to cold, that pressure rearranges matter, that gravity pulls everything toward the center. The lower mantle is geology without narrative. It is the planet doing what planets do, indifferent to observation, indifferent to consequence, indifferent to the thin film of biology trembling on its surface. And still it supports you. Still it shapes the ground you walk on. Still it drives the forces that build mountains and open oceans and slowly, imperceptibly, rearrange the face of the world. At a depth of 2,890 kilometers, the mantle ends. The transition is not gradual. It is one of the sharpest boundaries inside the Earth, a place where seismic waves change speed so abruptly that the first scientists to detect it assumed there must be an error in their calculations. There is no error. The core mantle boundary is real, and it separates two substances so different in composition and behavior that they might as well belong to different planets. Above it, solid rock, creeping under pressure, convecting over millions of years. Below it, liquid iron, flowing in currents measured in kilometers per year, generating the magnetic field that shields the surface from solar wind. The boundary between them is called the D-double prime layer, a region only a few hundred kilometers thick, where the properties of both rock and metal intermingle in ways still not fully understood. It is a place of extremes. The temperature there is estimated to be around 4,000 degrees Celsius, comparable to the surface of the sun. The pressure exceeds 1.5 million atmospheres. If you could stand at the core mantle boundary, which you cannot, you would be crushed and vaporized instantly, not by heat alone, but by the sheer weight of half the planet pressing down from above. The core mantle boundary is not a smooth surface. Seismic imaging reveals mountains and valleys in the rock above it, structures that dwarf anything on the Earth's surface. Some of these features rise several tens of kilometers, taller than Everest by a factor of 3 or more, though they are not mountains in any familiar sense. They are simply variations in the topography of the lowermost mantle, shaped by the interaction between the cold, dense rock sinking from above and the heat rising from the core below. The rock at this depth is not bridgmanite alone. It includes post-perovskite, a mineral phase that forms only under the most extreme conditions, stable only in the last few hundred kilometers of the mantle. Post-perovskite was predicted by theory before it was confirmed in experiments, another substance that exists in vast quantities, but has never been seen outside a laboratory. Its discovery was one of the triumphs of high-pressure mineral physics, proof that the equations governing atomic bonding could predict the behavior of matter, even at pressures no natural surface process can achieve. The heat flowing from the core into the mantle drives much of what happens above. The core is not cooling quickly, but it is cooling, and as it does, it releases energy that warms the base of the mantle and sustains the convection currents that move continents and open oceans. Some of that heat is primordial, left over from the Earth's formation, when countless smaller bodies collided and merged in a process so violent it melted the entire planet. Some of it comes from the decay of radioactive elements, particularly uranium and thorium, which may have sunk into the core early in Earth's history. Some of it comes from the crystallization of the inner core, a process that releases latent heat as liquid iron freezes into solid metal under the immense pressure at the planet's center. The core is a furnace, not because it burns, but because it stores and slowly releases the energy of the Earth's creation. That energy has nowhere to go but up. The outer core begins where the mantle ends, and it is the only truly liquid layer inside the Earth. It is not lava. It is not molten rock. It is iron, with smaller amounts of nickel and lighter elements like sulfur, oxygen, or silicon mixed in to lower its melting point. At the pressures found in the outer core, pure iron would be solid, but the presence of these lighter elements keeps it molten, allows it to flow. And flow it does in complex, turbulent patterns driven by the planet's rotation and by convection currents that rise from the hotter inner regions and sink near the mantle. These flows generate electric currents, and those electric currents generate the Earth's magnetic field, a process called the geodynamo. It is one of the most important phenomena on the planet, and it occurs entirely out of sight, driven by forces no human will ever witness directly. Without the geodynamo, the magnetic field would collapse. Without the magnetic field, the solar wind would strip away the atmosphere over millions of years, the way it stripped away the atmosphere of Mars. The outer core, invisible and inaccessible, is one of the reasons life exists on the surface. The outer core is thick. It extends from the base of the mantle at 2,890 kilometers down to a depth of 5,150 kilometers, a span of more than 2,000 kilometers. If the outer core were a separate planet, it would be larger than Mars. It contains more iron than all the structures humanity has ever built, more metal than could be mined from every asteroid in the solar system, and it is in constant motion, stirred by forces that operate on timescales ranging from years to millions of years. The magnetic field generated by the outer core is not static. It wanders. The North Magnetic Pole, the point toward which compasses point, drifts across the Arctic at speeds that have accelerated in recent decades, moving from Canada toward Siberia. The field itself reverses polarity every few 100,000 years on average, though the timing is irregular. During a reversal, the field weakens but does not disappear entirely. Compasses would not point north or south, but toward multiple, shifting poles. These reversals are recorded in the rocks of the ocean floor, in stripes of magnetized basalt that preserve the orientation of the field at the time they cooled. The pattern is symmetrical on either side of mid-ocean ridges, proof that the seafloor spreads and that the magnetic field has flipped many times over Earth's history. The core remembers nothing of these reversals. It simply continues, generating the field according to the physics of conducting fluids in motion, indifferent to the consequences above. To descend through the outer core would be to pass through a medium denser than any substance you have encountered on the surface, hotter than any furnace, moving in ways that would tear apart anything solid. There is no boundary you could touch, no floor you could stand on. The outer core is defined not by surfaces, but by gradients, by changes in density and temperature that occur over distances too large to perceive as transitions. It is an ocean, but not of water. It is metal, behaving as a fluid, flowing under conditions so alien to surface experience that intuition fails completely. And yet it is there beneath your feet, farther down than the height of the atmosphere above your head, supporting the mantle, driving the magnetic field, containing within it the final, deepest layer of the planet. The inner core is solid. This seems impossible. At the center of the planet, where the pressure is 3.5 million times greater than atmospheric pressure at sea level, where the temperature exceeds 5,000 degrees Celsius, the iron is not molten. It has crystallized. The pressure is so immense that it forces the atoms into a solid lattice despite the heat, locking them in place through sheer gravitational compression. The inner core is a sphere of iron roughly 1,200 kilometers in radius, suspended in the liquid metal of the outer core, isolated from the rest of the planet by thousands of kilometers of material that will never be crossed. It is the densest part of the Earth, the deepest destination, the final layer. And it was not discovered until 1936, when a Danish seismologist named Inge Lehmann noticed that seismic waves from earthquakes were behaving in ways that could only be explained if there was something solid at the center, something that reflected and refracted the waves in a pattern inconsistent with a fully liquid core. She was correct. The inner core exists, though no human sense will ever confirm it directly. The inner core is growing. As the Earth continues to cool, the outer core gradually loses heat to the mantle above, and as it cools, iron crystallizes out of the liquid and adds itself to the solid inner core. The process is slow. The inner core grows by roughly a millimeter per year, a rate so gradual that it would take 1,000,000 years to add a single kilometer to its radius. And yet, over the age of the Earth, this process has built a sphere larger than the Moon, a sphere that was not there when the planet formed. The early Earth had no inner core. The entire core was liquid, a churning sea of molten metal that gradually cooled and solidified from the center outward. The inner core is young compared to the planet, perhaps only 1 billion or 2 billion years old. Though the exact age is uncertain, it is still forming. It will continue to form for billions of years more, slowly consuming the outer core, growing larger as the planet cools, until eventually, far in the future, the entire core may solidify. By then, the geodynamo will have ceased, the magnetic field will have faded, the surface will be a different world, but that is not a future anyone will see. The inner core rotates. It does not rotate at the same speed as the rest of the planet. Seismic studies suggest it turns slightly faster, completing an additional rotation every few hundred to 1,000 years, though the measurements are difficult and the conclusions debated. The inner core is not rigidly attached to anything. It floats in the liquid outer core, held in place by gravity, but free to move relative to the mantle and crust above. Its rotation is driven by the magnetic field generated in the outer core, which exerts a torque on the solid iron, pulling it along. The result is a kind of differential motion, a slippage between the inner core and the outer layers of the planet, measurable only through changes in the travel time of seismic waves passing through it. The inner core is not stationary. It is not locked in place. It drifts, spins, and oscillates in ways that are only beginning to be understood. It is a planet within a planet, turning at its own pace, governed by forces unique to the deep. The structure of the inner core is not uniform. Seismic waves travel through it at different speeds depending on their direction, a phenomenon called anisotropy. Waves that pass through the inner core from pole to pole travel faster than waves that pass through it along the equator. This suggests the iron crystals are aligned, oriented preferentially in one direction, perhaps as a result of the immense pressure or the convective flows in the outer core that shaped the inner core as it grew. There may also be layers within the inner core, regions where the iron has different properties, different crystal structures, different histories. Some studies suggest there is an innermost inner core, a central region perhaps 300 kilometers in radius, where the anisotropy is even stronger, where the iron may be arranged in a different pattern. The evidence is tentative. The data are sparse. Earthquakes large enough and well placed enough to send clear signals through the very center of the Earth are rare, and each one provides only a narrow glimpse of the structure. But the suggestion is there, quiet and persistent, that even at the deepest point, the Earth is layered, complex, and not fully known. The temperature at the center of the Earth is hotter than the surface of the Sun. This is one of those facts that resists intuition, not because it is difficult to understand, but because it seems disconnected from experience. The Sun is a ball of fusing hydrogen, and its surface is merely the coolest part of it. The center of the Earth is hot for different reasons: primordial heat, radioactive decay, the release of gravitational energy as the planet compressed during its formation. But the comparison holds. If you could place a thermometer at the very center of the planet, it would register somewhere between 5,000 and 6,000 degrees Celsius, a temperature at which most materials would vaporize, but the iron remains solid, pressed into place by the weight of the world. The inner core is not glowing. It does not radiate light. It exists in darkness, surrounded by liquid metal, insulated by thousands of kilometers of rock and metal, never to be seen, never to cool enough in any time frame that matters to anything alive. To imagine descending to the inner core is to imagine a journey that cannot be taken. There is no path. There is no vehicle that could survive the heat and pressure. Even if you could somehow pass through the mantle, through the outer core, through the forces that would destroy any material known to science, you would arrive at a place without reference points, without up or down, without anything to see or touch or measure except the uniform, crushing presence of iron in all directions. The inner core is not a destination. It is not a place in the sense that places are meant to be visited. It is simply the center, the deepest point, the end of the descent, and it exists not for you but because the physics of planetary formation require it. Gravity pulls inward, pressure increases with depth, temperature rises, and at the very center, where the pressure is highest and the pull is equal in all directions, the densest material settles and solidifies, forming a core that will remain as long as the Earth exists. The Earth is 4.5 billion years old. This is not an estimate rounded for convenience. It is a measurement derived from radiometric dating of the oldest minerals ever found, tiny crystals of zircon extracted from ancient rocks in Western Australia, grains no larger than a human hair that have survived every upheaval the planet has experienced since they formed. Those crystals are 4.4 billion years old, which means they crystallized only 100 million years or so after the solar system itself came into being. They are older than the oldest rocks, older than the continents, older than the oceans. They are fragments of a world that no longer exists, preserved by chance and by their own chemical resilience. Everything else from that era is gone, recycled into the mantle, melted and reformed and mixed beyond recognition. But the zircons remain, and they tell a story of a planet that was molten, chaotic, bombarded by debris from space, and yet already beginning to cool, already forming a crust thin enough for minerals to crystallize within it. The deep structures you have descended through, the mantle, the core, the layers that make up nearly all of the planet, are older still, though no sample of them will ever be dated. They formed in the first tens of millions of years, when the Earth was not yet a sphere, but a growing mass of colliding planetesimals, each impact adding material and heat, each collision pushing the heaviest elements toward the center. The core is as old as the Earth itself. It has been there since the beginning and it will be there at the end. But age is not the same as permanence. The structures beneath the surface have changed. The mantle has convected, mixing slowly over billions of years, pulling cold material down and pushing hot material up in cycles that take hundreds of millions of years to complete. The core has cooled and differentiated, separating into liquid and solid regions, generating a magnetic field that has reversed polarity hundreds of times. The crust has been created and destroyed and created again, subducted and recycled in a process that leaves almost nothing of the original surface intact. The Earth you stand on is not the Earth that formed. It is a later version, remodeled and resurfaced countless times, every mountain range a temporary feature, every ocean basin a temporary structure, every continent a raft of low-density rock drifting on a slow current that has been flowing since before life arose. The planet is not static. It has never been static. But the changes occur so slowly that they are invisible on human timescales, imperceptible on the timescales of civilizations, noticeable only when you compare the world as it is now to the world as it was hundreds of millions of years ago, when the continents were arranged differently, when the climate was different, when the species alive on the surface bore no resemblance to anything living today. The deep changes even more slowly than the surface. The mantle creeps at centimeters per year. The inner core grows at millimeters per year. The outer core flows faster, but even its currents are measured in kilometers per year, speeds that would be considered glacial if they occurred on the surface. These are not processes you can watch. They are not processes anyone will ever watch. They unfold over spans of time too vast to fit into any narrative structure that makes sense to a mind evolved to track days and seasons. A convection cycle in the mantle might take 200 million years. That is longer than the time since the continents last assembled into a supercontinent. It is longer than the age of the Atlantic Ocean. It is longer than the time since the dinosaurs appeared. And it is a single cycle, one turn of the current, one rise and fall of material within a system that has been operating for 4.5 billion years and will continue operating for billions more. The deep does not hurry. It has no reason to. And yet it is not separate from the surface. The heat rising from the core drives the convection in the mantle. The convection in the mantle drives the motion of the plates. The motion of the plates builds mountains, opens ocean basins, triggers earthquakes and volcanoes, shapes coastlines and climates. The deep is the engine, invisible and inaccessible, but its effects ripple upward, shaping the world in ways that seem immediate and dramatic, but are simply the surface expression of processes occurring far below. Every earthquake is a reminder that the planet is active. Every volcano is evidence that the interior is still hot. Every slow drift of a continent is proof that the mantle is still moving, still convecting, still transferring heat from the core to the surface, in a cycle that has continued without pause since the Earth was young. You do not feel the deep. You feel what the deep does, translated through thousands of kilometers of rock and metal, filtered and softened and slowed by distance, but never entirely absent. The ground beneath you is not stable. It has never been stable. It is simply moving too slowly for you to notice without instruments, without decades or centuries of observation, without the kind of patient attention that matches the patience of the planet itself. There is no way to witness the deep directly. No camera will ever record it. No probe will ever sample it. The mantle is too thick, the temperature's too high, the pressure's too extreme. Even the crust, so thin and accessible compared to the rest of the planet, resists penetration. The Kola Superdeep borehole, the deepest hole ever drilled, reached 12 kilometers after more than 20 years of effort, and that is less than half of 1% of the distance to the center. If you wanted to drill to the core, assuming you had a drill bit that could survive the conditions, it would take not decades but millennia, and the hole would collapse behind you as you descended, the rock flowing back into place under the pressure, sealing itself shut. The Earth does not allow intrusion. It does not invite exploration. It simply exists, layered and hidden, offering only indirect evidence of what lies beneath: seismic waves, magnetic fields, the occasional eruption of material from depths great enough to carry fragments of the mantle to the surface. These are not invitations. They are accidents, moments when the boundary between the deep and the shallow becomes temporarily permeable, allowing a glimpse of what is otherwise sealed away forever. Everything known about the deep comes from inference. No one has seen the mantle. No one has touched the core. The entire interior of the planet is a construction built from fragments of indirect evidence and held together by mathematics and physics. When an earthquake occurs, it sends waves through the Earth, and those waves travel at different speeds through different materials. Seismologists measure the arrival times of these waves at stations scattered across the globe, and from those measurements, they can deduce the properties of the material the waves passed through, its density, its rigidity, its temperature, its phase. It is the same principle as medical imaging, but the patient is the planet, and the signals are not controlled but opportunistic, generated by the Earth's own instability. Every earthquake is an experiment. Every tremor is data. Over more than a century, these data have accumulated into a picture, detailed enough to distinguish layers, to map boundaries, to identify regions of anomalous temperature or composition. The picture is not a guess. It is constrained by observation, tested against predictions, refined as new earthquakes occur and new instruments are deployed. But it is still a picture built from echoes, from waves that traveled through places no human will ever visit, interpreted through models that must account for pressures and temperatures no laboratory can sustain indefinitely. The certainty with which we speak of the mantle and core is earned, not assumed. The existence of the core was inferred by Richard Oldham in 1906, when he noticed that seismic waves from earthquakes on one side of the planet arrived late or not at all at stations on the opposite side, as if something in the middle was slowing them down or blocking them entirely. He proposed a liquid core, and he was correct, though he had no way to measure its size or composition directly. The core-mantle boundary was mapped by Benno Gutenberg in 1914, using the same methods, measuring the travel times of seismic waves and calculating where they must have refracted or reflected to produce the observed pattern. The inner core was discovered by Inga Lehmann in 1936, when she identified faint seismic arrivals that could only be explained by the presence of something solid at the center, something that reflected waves back toward the surface. Each of these discoveries was a triumph of patience and logic, a demonstration that the invisible could be mapped if the right questions were asked and the right measurements taken. The deep was not handed to science. It was pried loose, layer by layer, through the careful analysis of events no one controlled, and the gradual construction of a model consistent with all available evidence. Laboratory experiments provide another form of evidence. Scientists can compress minerals to the pressures found in the mantle or core using diamond anvil cells, devices that squeeze tiny samples between two diamonds and apply forces equivalent to millions of atmospheres. They can heat those samples with lasers, simulating the temperatures of the deep, and observe how the minerals behave, when they melt, when they change phase, how their crystal structures rearrange under stress. These experiments are difficult. The samples are smaller than grains of sand. The conditions are extreme and hard to maintain. The measurements are indirect, often relying on X-ray diffraction or spectroscopy to determine the state of the material inside the cell. But over decades, experimentalists have recreated the conditions of the mantle and even the outer core in laboratories, confirming that the mineral's seismology suggests should exist at those depths do in fact exist, that their properties match the predictions that the model holds. The deep can be tested not by going there but by bringing pieces of it, or approximations of it, to the surface and subjecting them to the forces that govern the interior. Meteorites offer another window. The Earth formed from the same material as the asteroids and comets that still orbit the Sun, and some of those objects have remained largely unchanged since the solar system's formation. When they fall to Earth, they carry with them clues about the composition of planetary interiors. Iron meteorites, in particular, are thought to be fragments of the cores of small planets that formed early and were later shattered by collisions. Their chemistry, mostly iron and nickel, with trace amounts of lighter elements, matches the inferred composition of the Earth's core. Stony meteorites contain minerals similar to those found in the mantle. By studying meteorites, scientists can constrain the bulk composition of the Earth, estimate how much of each element exists in the planet as a whole, and infer how those elements are distributed between the crust, mantle, and core. Meteorites are not pieces of the Earth, but they are pieces of the process that made the Earth, and they provide a form of ground truth, a reference against which models of the interior can be checked. There is also theory. The equations governing heat transfer, fluid dynamics, and the behavior of materials under pressure are well understood, and they can be applied to the Earth's interior to predict how it should behave. Computer simulations of mantle convection, for instance, can reproduce the patterns of plate motion observed at the surface, suggesting that the models capture something essential about the deep, even if the details remain uncertain. Simulations of the geodynamo can generate magnetic fields similar to the Earth's, confirming that the outer core is capable of sustaining the field through the motion of conducting fluid. These simulations are not proof in the sense that a laboratory experiment is proof, but they are consistent with observation, and they allow scientists to explore scenarios that cannot be tested directly. What happens if the mantle is slightly hotter, or if the inner core grows faster, or if the magnetic field reverses. Theory extends the reach of knowledge beyond what can be measured, allowing predictions and insights that observation alone cannot provide. And yet, for all this effort, the deep remains largely unknown. The resolution of seismic imaging is limited. The experiments can only approximate the conditions of the interior. The simulations rely on assumptions that may not hold in all circumstances. There are questions that remain unanswered, not because scientists have failed to ask them, but because the data are insufficient or the physics are too complex. The exact composition of the outer core is uncertain. The presence of an innermost inner core is debated. The details of how mantle plumes form and rise are not fully understood. The deep is better mapped now than it has ever been, but it is not fully known, and it may never be fully known, because the barriers to direct observation are not merely technical but fundamental. The interior is too hot, too deep, too remote. It will always be a place constructed from inference, glimpsed through waves and experiments and theory, but never seen, never touched, never confirmed by the kind of direct experience that satisfies human intuition. The words solid and liquid lose precision when applied to the deep. On the surface, these terms describe states that can be easily distinguished. Water is liquid, ice is solid. The boundary between them is sharp, occurring at 0 degrees Celsius under normal pressure, and the transition is fast. You can watch ice melt. You can watch water freeze. The change happens within minutes or hours, and the difference is obvious. But in the mantle, these distinctions blur. The rock there is solid in the sense that it has a crystal structure, that its atoms are locked into place, that it will not flow if you push on it over seconds or minutes or years. But it is not solid the way granite is solid. It is not rigid. Over geological time, it flows, deforming plastically under stress, moving in response to forces so gradual they cannot be felt. The mantle convects. It rises in some places and sinks in others. It behaves like a fluid, but it is not a liquid. It is something else, a state of matter that does not fit neatly into the categories taught in school, where materials are either one thing or another, and the transitions between them are clear. This is not unique to the Earth. All materials behave this way if given enough time and pressure. Glass, often said to be a liquid because old windows are thicker at the bottom than the top, is not actually flowing. That is a myth. But glass would flow given enough time, given enough stress, given conditions where the atoms could rearrange without breaking the bonds that hold them in place. Steel flows, diamond flows. Everything flows if the timescale is long enough and the forces are strong enough. The mantle is simply operating on timescales long enough that its flow becomes noticeable, becomes measurable, becomes the dominant mode of behavior. It is solid on human timescales and liquid on geological timescales, and there is no contradiction in that. It is simply a reminder that the categories used to describe the world are not absolute, but contextual, dependent on the scale at which you are observing. The pressure in the deep changes everything. At the surface, pressure is something you barely notice. It is the weight of the atmosphere, roughly 1 kilogram per square centimeter, pressing down on you from all sides. You are built to withstand it. You do not feel it. Even underwater at depths accessible to divers, the pressure increases by only 1 atmosphere for every 10 meters of depth. It is noticeable, but manageable. In the deep Earth, pressure is not measured in atmospheres but in gigapascals, units that represent forces so large they compress atoms, force electrons into tighter orbits, change the way chemical bonds form. At the base of the mantle, the pressure is 140 gigapascals, equivalent to 1.5 million atmospheres. At the center of the core, it is 360 gigapascals, more than 3.5 million atmospheres. These are not forces that can be visualized. They are not forces that can be understood through analogy to anything experienced in daily life. They are simply numbers, abstract and enormous, representing conditions so extreme that matter behaves in ways that seem alien. Under these pressures, atoms pack together more tightly than they do at the surface. The spaces between them shrink. The electrons that normally keep atoms apart are forced closer to the nuclei. This is why the core is so dense. It is not made of exotic materials. It is made of iron, the same element found in nails and cars and blood. But at the pressures of the core, iron is compressed to nearly twice the density it has at the surface. A cubic meter of core material would weigh more than 13,000 kilograms, far heavier than the same volume of iron at atmospheric pressure. Density is not a fixed property of matter. It changes with conditions, and in the deep, those conditions are so far removed from anything familiar that the materials themselves become unrecognizable, behaving in ways that can only be predicted by solving equations that describe the quantum mechanical interactions of atoms under stress. Temperature compounds the strangeness. At the surface, heat makes materials expand. It increases the motion of atoms, loosens bonds, and eventually causes melting. But in the deep, the effect of temperature is counteracted by pressure. The inner core is hotter than the surface of the sun, but it is solid because the pressure is so great that the atoms cannot move freely, cannot escape the lattice that holds them in place. The melting point of iron increases with pressure. At the center of the Earth, iron does not melt until it reaches temperatures well above 5,000 degrees Celsius, far higher than it would melt at the surface. This is why the inner core is solid and the outer core is liquid. The temperature gradient in the core is shallow, increasing only slightly with depth, but the pressure gradient is steep, and at a certain depth, around 5,150 kilometers down, the pressure becomes high enough that iron solidifies despite the heat. The boundary between the inner and outer core is not a temperature boundary. It is a pressure boundary, a place where the same material exists in two different states because the forces acting on it are different. The deep does not obey the rules you learned by living on the surface. It does not behave the way you expect materials to behave. It is not intuitive, and it cannot be made intuitive because intuition is built from experience, and no one has experience with pressures measured in gigapascals or temperatures measured in thousands of degrees. The deep is a regime where the familiar properties of matter, hardness, fluidity, melting point, density, become variables, dependent on conditions that cannot be reproduced outside of specialized laboratories or the interiors of planets. To understand the deep is to accept that it operates according to principles that are correct but alien, governed by physics that applies everywhere but is only noticeable under extremes. The surface is the exception, not the rule. The crust is a thin zone where pressures are low enough and temperatures mild enough that matter behaves in simple, predictable ways. The deep is the norm, the condition that prevails throughout most of the planet, where simplicity breaks down and everything becomes contingent on forces too large to imagine. And yet, the deep is stable. It does not change quickly. The pressures and temperatures at any given depth have remained roughly constant for billions of years. The convection in the mantle is slow and steady. The crystallization of the inner core proceeds at a predictable rate. The outer core flows, but the flow is orderly, driven by the same forces that have driven it since the core formed. There is no chaos in the deep. There is no instability. The forces are immense, the conditions extreme, but the system is in equilibrium, or as close to equilibrium as a cooling planet can be. The deep changes, but it changes gradually, incrementally, along trajectories that are predictable, given enough understanding of the physics involved. It is not a place of violence. It is a place of patience, where pressures that would destroy anything at the surface are simply the background, the default, the condition that has always existed and will continue to exist long after the surface has changed beyond recognition. The heat in the deep is not evenly distributed. The core is hotter than the mantle, and the mantle is hotter than the crust, but the gradient is not uniform. Heat flows from regions of high temperature to regions of low temperature, and it flows in several ways. In the core, where the iron is liquid and convecting, heat is carried by the motion of the fluid itself, rising currents bringing hot material upward and sinking currents pulling cooler material downward. In the mantle, heat moves through convection as well, but more slowly, because the rock is solid and can only flow over geological timescales. And in the crust, heat moves primarily through conduction, atoms transferring energy to their neighbors through vibrations, a process so slow that it takes millions of years for heat generated at the base of the crust to reach the surface. The deep is losing heat, and it has been losing heat since the planet formed, radiating energy into space at a rate of about 47 terawatts, roughly 3 times the total energy consumption of human civilization. That energy comes from the cooling of the interior, from the decay of radioactive elements, and from the crystallization of the inner core, and it flows upward continuously, invisibly, driving everything that happens on the surface. Volcanoes are the most visible expression of the deep's heat. When magma rises through the crust and erupts at the surface, it brings with it material from depths of tens or even hundreds of kilometers. Molten rock that was part of the mantle until tectonic forces or pressure changes caused it to melt and migrate upward. The lava that flows from a volcano is not the mantle itself, but it is derived from the mantle, a fragment of the deep made temporarily accessible, carrying with it gases and minerals that would otherwise remain buried. Volcanic eruptions are rare on human timescales, but they are continuous on geological timescales. Somewhere on Earth, a volcano is erupting right now. Somewhere, magma is rising through the crust, pooling in chambers, fracturing the rock above it, preparing to break through. The energy for these eruptions comes from the heat of the mantle, stored there for billions of years, and released slowly, incrementally, in bursts that reshape landscapes and alter climates, but do not significantly cool the deep. A single eruption, even a large one, releases only a tiny fraction of the mantle's heat. The mantle is vast, and its heat content is enormous. It will take billions of years for the planet to cool enough that volcanism ceases entirely. Mid-ocean ridges are another outlet. These are underwater mountain ranges, where tectonic plates pull apart and new crust is formed, magma rising from the mantle to fill the gap. The process is continuous. At any given moment, new crust is being created at ridges around the world, adding material to the ocean floor at a rate of a few centimeters per year. The magma that forms this new crust comes from the upper mantle, drawn upward by the reduction in pressure as the plates separate. It does not erupt explosively the way volcanoes on land often do. It oozes out, cools quickly in the cold seawater, and solidifies into basalt, a dense, dark rock that makes up most of the oceanic crust. The ridges are not dramatic in the way volcanic peaks are dramatic. They are hidden, submerged, visited only by robotic submersibles, and studied primarily through sonar and seismic imaging. But they are among the most geologically active places on the planet, zones where the boundary between the deep and the surface is thinnest, where the mantle is almost exposed, covered by only a few kilometers of newly formed crust. Geothermal gradients measure how temperature increases with depth in the crust. On average, the temperature rises by about 25 to 30 degrees Celsius for every kilometer of depth, though the exact rate varies depending on location and the composition of the rock. In tectonically active regions, where magma is close to the surface, or where the crust is thin, the gradient can be much steeper. In stable continental interiors, where the crust is thick and old, the gradient is gentler. These gradients are not large by the standards of the deep, but they are measurable, and they reflect the flow of heat from the interior to the surface. Geothermal energy is not free energy. It is the planet's stored heat, leaking out slowly, and the rate at which it leaks depends on the conductivity of the rock and the distance the heat must travel. In some places, the heat flow is high enough to be harnessed for power generation, tapping into reservoirs of hot water or steam heated by proximity to magma. In most places, the heat flow is too diffuse, too spread out, to be useful for anything other than warming the ground very slightly. The surface does not feel the deep's heat directly. The sun provides vastly more energy to the surface than the interior does. Solar radiation warms the air, the oceans, and the land, driving weather and climate and sustaining life. The heat from the deep, by comparison, is negligible in terms of its direct contribution to surface temperatures. If the sun were extinguished, the surface would freeze within weeks, and the heat from the interior would do nothing to prevent it. The deep is not a heater. It is not keeping you warm. But it is driving the processes that shape the surface: plate tectonics, volcanism, the recycling of crust, the opening and closing of ocean basins. Without the heat from the deep, the planet would be geologically dead. The continents would not drift, mountains would not rise. Earthquakes and volcanoes would cease. The surface would be static, frozen not by cold, but by the absence of the forces that have reshaped it continuously for billions of years. The deep is not visible, but its influence is everywhere. Every coastline, every mountain range, every island, every ocean trench is a product of the heat flowing out from below, the energy of the interior translated into motion, into uplift, into the slow rearrangement of the crust. And the heat will continue to flow. The Earth is not cooling rapidly. The processes that generate heat, the decay of uranium, thorium, and potassium, the crystallization of the inner core, are ongoing and will continue for billions of years. The planet is warmer now than it will be in the future, but it is cooler now than it was in the past, and the cooling is so gradual that it is not something any species will ever experience as a change. The heat flow from the deep is a constant, a background process that has been operating since the planet formed and will continue operating until the core solidifies and the mantle stops convecting. Events so far in the future that they belong to a different era entirely. A time when the sun itself will have changed, when the surface will be uninhabitable for reasons unrelated to geology. For now, the deep is hot, and it will remain hot, and the heat it contains is enough to power the tectonic processes that define the planet for as long as those processes matter to anyone. The mantle contains water. Not water as you know it, not liquid, not flowing in underground rivers or pooling in hidden reservoirs. The water in the mantle is bound within the crystal structure of minerals, trapped in the lattice of atoms that make up the rock. Hydroxyl groups, molecules of hydrogen and oxygen chemically bonded to silicon, magnesium and other elements, exist in concentrations measured in parts per million or parts per thousand. These are trace amounts by weight, but the mantle is so vast that even trace amounts add up. The total water content of the mantle may equal or exceed the volume of all the Earth's oceans combined. It is hidden water, structural water, water that cannot be extracted or seen or felt, but water nonetheless, distributed throughout the deep in quantities that dwarf the surface reservoirs. This water arrived with the planet's formation, delivered by asteroids and comets that carried ice and hydrated minerals, and it has been cycling through the Earth ever since, subducted into the mantle when oceanic plates sink, released back to the surface through volcanic eruptions, moving between the deep and the shallow in a rhythm measured in hundreds of millions of years. The presence of water in the mantle changes everything. Water lowers the melting point of rock. A mantle that contains even small amounts of water will begin to melt at temperatures where dry rock would remain solid. This is why subduction zones are so volcanically active. When an oceanic plate descends into the mantle, it carries with it seawater that has permeated the crust, water trapped in pores and fractures, and chemically bound in minerals altered by contact with the ocean. As the plate sinks and heats, the water is released, rising into the overlying mantle and lowering its melting point, creating magma that rises to form volcanic arcs, chains of volcanoes like those in the Andes, Japan, and the Pacific Northwest. The water does not melt the rock directly. It acts as a catalyst, a substance that changes the conditions under which melting occurs, allowing the mantle to produce magma at depths and temperatures where it otherwise would not. Without water, the mantle would be drier, colder, less prone to melting. The surface would be less volcanic, the crust thicker, the recycling of materials slower. Water is not an accessory. It is integral to the way the planet operates, and most of it is not on the surface but in the deep, cycling through the mantle in ways that are only beginning to be understood. Other volatiles exist in the mantle as well. Carbon, for instance, is present in small amounts stored in minerals or dissolved in the rock, and it too is cycled through subduction and volcanism. When carbonate minerals are subducted, they are carried into the mantle, where heat and pressure break them down, releasing carbon dioxide that can be incorporated into magma and eventually erupted at the surface. This is part of the carbon cycle, the slow exchange of carbon between the atmosphere, the oceans, the crust, and the mantle. Most of the Earth's carbon is not in the atmosphere or the biosphere. It is in the deep, locked away in forms that do not interact with the surface on human timescales, but that can be released over geological time through volcanic activity. The amount of carbon dioxide released by volcanoes each year is small compared to human emissions, but over millions of years, volcanic outgassing has been a major source of atmospheric carbon, balancing the loss of carbon to weathering and burial in sediments. The deep is not separate from the climate system. It is part of it, a reservoir that exchanges material with the surface on timescales too slow to notice, but too important to ignore. Nitrogen, sulfur, noble gases, all of these are present in the mantle, inherited from the materials that built the planet or delivered by impacts early in Earth's history. They exist in trace amounts, but the mantle is so large that trace amounts are significant. The atmosphere itself is thought to have been outgassed from the interior over geological time, volcanic eruptions gradually releasing gases trapped in the mantle and building up the thin envelope of air that now surrounds the planet. The composition of the atmosphere is not fixed. It has changed over the Earth's history, shaped by the balance between volcanic outgassing, which adds gases, and processes like weathering and the burial of organic matter, which remove them. The deep has been exhaling into the atmosphere for billions of years, and it will continue to exhale as long as there is heat to drive volcanism, as long as the mantle convects and magma rises through the crust. You are breathing air that came from the deep, molecules that were once part of the mantle, released through eruptions that occurred millions or billions of years ago, cycled through the biosphere and the oceans, and eventually inhaled, exhaled, and inhaled again by countless organisms. The boundary between the surface and the deep is not impermeable. It is porous, allowing the slow exchange of material in both directions, a flux that maintains the planet in a state that is neither fully closed nor fully open, but somewhere in between. The transition zones in the mantle, regions at specific depths where minerals change phase, act as barriers or conduits for this exchange. At 410 kilometers depth, minerals in the upper mantle transform into denser structures that can hold more water. At 660 kilometers, they transform again, releasing water or allowing it to pass deeper into the lower mantle. These transitions are not abrupt in space. They occur over tens of kilometers, but they are sharp in terms of their effect on the behavior of the mantle. Material sinking from above may stall at these depths, accumulate and eventually break through, or it may be deflected, spreading laterally before continuing its descent. Water released at these depths can migrate upward or downward, influencing where melting occurs and how much magma is produced. The mantle is not a simple conveyor belt, carrying material from the surface to the deep and back again. It is a complex system with layers and barriers and pathways that depend on composition, temperature and pressure, a system where small variations in any of these factors can have large effects on how material moves and where it ends up. There are portions of the mantle that may not have mixed with the surface in billions of years. Geochemical analysis of volcanic rocks sometimes reveals isotopic signatures that suggest the source material has been isolated from the convecting upper mantle for a very long time, perhaps since the planet's formation. These are called primordial reservoirs, pockets of mantle that have retained their original composition, untouched by the recycling of crust and the injection of subducted material. They may exist in the deep lower mantle, too far down and too sluggish to participate in the faster convection occurring above, or they may be scattered throughout the mantle in regions that, by chance or by the specific dynamics of flow, have avoided mixing. Their existence is debated and their size and distribution are unknown, but the possibility that parts of the Earth's interior remain unchanged since the beginning is striking. The deep does not forget. It may not remember in any conscious sense, but it holds within it records of the planet's formation, traces of the earliest processes, materials that have survived 4.5 billion years of heat and pressure and motion without being thoroughly mixed into the average composition of the mantle. The deep is ancient, not just in age but in memory, preserving in its structure and chemistry the conditions of a time no surface process can access. The timescales of the deep are not human timescales. A convection cycle in the mantle takes 200 million years. The inner core grows by 1 millimeter each year. The magnetic field reverses polarity every few 100,000 years on average, though the intervals vary widely and unpredictably. These are not durations that fit into any framework built from experience. You cannot wait for them. You cannot observe them. You can only infer them from evidence accumulated over decades or centuries of study, measurements taken by instruments that detect changes too subtle and too slow to be felt. The deep does not operate on the scale of lifetimes or civilizations. It operates on the scale of species, of epochs, of eons. A mountain range rises over tens of millions of years. An ocean basin opens over 100 million. A continent drifts from one pole to another over periods longer than complex life has existed. And all of this is driven by processes in the deep, by the slow churn of the mantle, by the cooling of the core, by forces that have been active since the planet was young and will remain active long after the surface has been reshaped beyond recognition. To say the Earth is old is to state an abstraction. 4.5 billion years is a number, but it is not a duration you can feel. The oldest human artifacts are a few 100,000 years old. The oldest civilizations arose only a few thousand years ago. Recorded history spans mere millennia. Even the oldest living organisms, trees that have stood for thousands of years, are young compared to the age of the rocks they grow on, and those rocks are young compared to the age of the planet. The entire span of human existence is a flicker, a moment, a fraction of a percent of the Earth's history. And yet, during that flicker, the deep has continued exactly as it always has. The mantle has convected, the core has cooled, the inner core has grown. Continents have drifted centimeters or meters, distances you could walk in minutes, but that represent the sum of motion occurring continuously, incrementally, at rates too slow to detect without instruments. The deep does not pause, it does not wait, it simply continues, indifferent to the presence or absence of observers, operating according to laws that do not depend on attention or understanding. There is a kind of patience in this that is not patience at all, because patience implies waiting, and the deep is not waiting. It is simply being, existing in a state where time is not a constraint but a dimension, a variable that stretches across billions of years without urgency or hurry. The processes occurring in the mantle are not slow because they are lazy or inefficient. They are slow because the forces involved are immense, the distances vast, and the materials resistant. Rock does not flow quickly under any circumstances. Convection in the mantle proceeds at the maximum rate, allowed by the viscosity of the rock and the temperature gradient driving it. It is not slow by choice. It is slow by necessity, constrained by the properties of matter under extreme pressure and heat. And yet over the lifespan of the planet, this slowness is enough. The mantle has mixed, the crust has been recycled, the continents have assembled and dispersed multiple times. Slowness does not mean inactivity. It simply means that activity occurs on a scale where human lifespans are irrelevant. You are living on the surface of a planet in motion. The ground beneath you is drifting, carried by currents in the mantle that move at the speed your fingernails grow. If you could stand in the same spot for 1,000,000 years, the landscape around you would change unrecognizably. Mountains would rise or erode. Coastlines would shift. The climate would change as the continents move to different latitudes, altering ocean currents and atmospheric circulation. And if you stood there for 100 million years, the continent itself would have moved thousands of kilometers, perhaps colliding with another landmass, perhaps splitting apart. The map of the world is not fixed. It is a snapshot, a single frame in a process that has been ongoing for billions of years and will continue for billions more. The geography you know, the arrangement of continents and oceans that defines the present, is temporary, no more permanent than the weather, though its changes occur over timescales so long that they might as well be eternal from any perspective that matters to a human life. The deep is not aware of this. It does not know that the surface exists. It does not know that life has arisen, that ecosystems have formed, that species have evolved and gone extinct in cycles spanning millions of years. The mantle convects because heat flows from hot to cold. The core generates a magnetic field because conducting fluids in motion generate magnetic fields. These are not actions taken with purpose. They are consequences of physical laws, outcomes that follow inevitably from the conditions that exist in the deep. The planet is not alive, despite the occasional metaphor that describes it as such. It is a ball of rock and metal, governed by gravity and thermodynamics, cooling slowly over billions of years, losing heat to space in a process that will eventually render it geologically inert. But that endpoint is so far in the future that it has no bearing on the present. For now, the planet is active, dynamic, and the deep is the engine driving that activity, not because it chooses to, but because it must, because the laws of physics leave it no other option. There is a paradox in trying to comprehend the deep. You can describe it, you can measure it, you can model its behavior and predict its future evolution with reasonable accuracy. But you cannot experience it. You cannot stand in the mantle. You cannot watch the inner core grow. You cannot observe a convection cycle from beginning to end. The deep exists at a remove, separated from direct perception by distance, by heat, by pressure, by time. It is knowable, but only abstractly. You can hold the knowledge of it in your mind, understand its properties and its role in shaping the planet, but that knowledge is mediated, constructed from indirect evidence and mathematical models. It is not the same as knowing a place by visiting it, by standing in it, by feeling it around you. The deep is a place that exists only as a concept, a set of data points and equations that describe something real but inaccessible. And yet, it is there. It is as real as the ground beneath your feet, more real in a sense, because it makes up nearly all of the planet, because it is the foundation upon which the surface rests, the engine that drives the forces shaping the crust. The deep is not imaginary. It is simply beyond reach. The magnetic field generated by the outer core is invisible. You cannot see it. You cannot feel it. A compass needle responds to it, swinging to point north, but the field itself leaves no mark on your senses. It is not a solid structure. It is not a substance. It is a pattern of force, lines of magnetic flux that extend from the planet's interior out into space, forming a bubble called the magnetosphere that shields the Earth from the solar wind. The solar wind is not wind in the ordinary sense. It is a stream of charged particles, electrons, protons, ions, ejected from the sun at speeds of hundreds of kilometers per second, carrying energy and momentum enough to strip away an atmosphere if given the chance. Mars lost its atmosphere this way. Its magnetic field faded billions of years ago, and without that protection, the solar wind eroded the thin envelope of gas that once surrounded it, leaving behind a cold, dry world where the surface pressure is less than 1% of Earth's. The Martian core cooled, the dynamo stopped, the field collapsed, and the atmosphere followed, thinned and scattered into space over millions of years, a slow bleeding that left the planet inhospitable to life as we know it. Earth's magnetic field is not permanent. It has reversed many times, the north and south magnetic poles flipping positions in events that take thousands of years to complete. During a reversal, the field does not vanish entirely, but it weakens, becomes more complex, splitting into multiple poles that shift and migrate before stabilizing into a new configuration with opposite polarity. The last reversal occurred roughly 780,000 years ago. The next one could begin tomorrow, or it could be delayed for hundreds of thousands of years more. There is no pattern, no regularity to the timing. Reversals are a natural part of the geodynamo's behavior, an emergent property of the turbulent, chaotic flow of molten iron in the outer core. They leave no lasting damage. Life survived previous reversals, though the fossil record is not detailed enough to say whether there were temporary effects on ecosystems or species, particularly sensitive to magnetic orientation. The field weakens during a reversal, and more cosmic rays and solar particles reach the surface, but the atmosphere absorbs most of the radiation, and the increase is not catastrophic. The deep continues generating the field, even as it reorganizes, and eventually the new configuration stabilizes, and the magnetosphere reforms, and the protection resumes. The field is not static between reversals either. It changes strength and orientation over decades and centuries, drifting and fluctuating in response to changes in the flow of the outer core. The North Magnetic Pole, which is actually the South Pole of the Earth's magnetic field due to a historical naming convention, has been moving across the Canadian Arctic towards Siberia at an accelerating rate in recent decades, now traveling more than 50 kilometers per year. This drift is not a precursor to a reversal, or at least not necessarily. It is simply the field responding to changes in the currents deep below, shifts in the pattern of convection that are driven by the cooling of the core and the complex dynamics of a rotating, conducting fluid under the influence of the planet's spin. The magnetic field is a window into the deep, one of the few ways the interior makes its presence known without earthquakes or eruptions. By studying how the field changes over time, scientists can infer properties of the outer core, its flow patterns, its composition, the strength of the forces driving the dynamo. The field is not just a protective shield. It is a signal, a trace of processes occurring thousands of kilometers below, transmitted through the planet and into space where satellites can measure it. The field has existed for most of Earth's history. Evidence from ancient rocks suggests it was present at least 3.5 billion years ago, possibly earlier, though the strength and stability of the early field are uncertain. This means the geodynamo has been operating, continuously or nearly so, for the vast majority of the planet's existence through every era of geological and biological change, through the rise of the first single-celled organisms, the oxygenation of the atmosphere, the evolution of complex life, the colonization of land, the mass extinctions, the rise and fall of species too numerous to count. The field has been there, generated by the motion of iron in the core, driven by heat that has been flowing out of the planet's interior since it formed. Without the field, the history of life might have been very different. The atmosphere might have been stripped away early, before life had a chance to take hold, or it might have persisted long enough for life to arise but not long enough for it to evolve into anything complex. The field is not incidental. It is foundational, and it is powered by the deep, by the energy stored in the core and released slowly over billions of years. You do not think about the magnetic field. You do not wake up grateful that it exists. It is invisible, unnoticed, taken for granted in the way all essential things are taken for granted until they are absent. And yet it is there, always, a product of the deep's motion, a consequence of the planet's structure and history. The outer core is flowing right now, convecting, generating currents, and those currents are generating the field that extends around you, around the atmosphere, out into space where it deflects the solar wind and funnels charged particles toward the poles, creating auroras when they collide with the upper atmosphere. The auroras are beautiful, but they are also a reminder. They are visible evidence of the interaction between the sun and the earth, between the solar wind and the magnetosphere, between the surface and the deep. The light you see in an aurora is powered by the sun, but it is shaped by the magnetic field, and the field is shaped by the motion of iron thousands of kilometers below. The deep is not separate. It is connected to everything, even to phenomena you associate with the sky, with space, with the sun. The core will cool eventually. The inner core will grow, consuming more of the outer core, and the volume of liquid iron available to generate the field will shrink. At some point, perhaps in 1 billion years, perhaps in several billion, the dynamo will weaken and then stop. The field will fade. The protection it provides will be lost. But by then the sun will have changed too, grown hotter and brighter, and the surface of the earth will be uninhabitable for other reasons. The timing is uncertain, but the outcome is not. The planet is cooling, and cooling leads to solidification, and solidification ends the dynamo. The deep is not eternal in its activity. It is sustained by heat, and heat is finite, even when the quantities are vast. The core is losing energy, radiating it into the mantle, which radiates it into the crust, which radiates it into space. The process is irreversible. The planet will not reheat. There is no external source of energy large enough to reverse the cooling. The deep is on a trajectory, a slow march toward quiescence, and the magnetic field is a transient phenomenon, something that exists now and will exist for a long time, but will not exist forever. The scale of the deep is difficult to hold in mind. Numbers can describe it: 6,371 kilometers from the surface to the center, 2,900 kilometers of mantle, 3,000 kilometers of core. But numbers do not convey the experience of distance or depth because there is no experience to convey. You have never descended 100 kilometers. You have never felt the pressure of 10,000 atmospheres. You have never stood in rock hot enough to glow if it were not opaque. The deep is not a place you can imagine yourself into. It resists visualization, not because it is abstract, but because it is too concrete, too specific in its extremes, too unlike anything you have encountered or could encounter. Trying to imagine the mantle is like trying to imagine a color you have never seen. The components are there, rock, heat, pressure, but they do not assemble into a coherent picture because the scale and the conditions warp them into something unfamiliar. And yet the deep is not alien. It is made of the same elements that make up the surface. Silicon, oxygen, iron, magnesium, these are common elements, abundant throughout the solar system, present in the crust and the mantle and the core, in different proportions and different forms, but fundamentally the same substances. The iron in your blood came from a supernova, and so did the iron in the core. The oxygen you breathe was forged in stars, and so was the oxygen bound in the minerals of the mantle. The materials are shared. What differs is the arrangement, the conditions, the forces acting on those materials. The deep is not another world. It is the same world, just deeper, subject to pressures and temperatures that transform familiar substances into unfamiliar states. The strangeness of the deep is not a strangeness of composition, but a strangeness of circumstance. It is what happens to rock when you bury it under thousands of kilometers of more rock. It is what happens to iron when you compress it and heat it and set it in motion within a rotating sphere. The deep is ordinary matter under extraordinary conditions, and the conditions are extraordinary only because the planet is large enough to generate them. The surface is the exception, not the deep. Most planets and moons in the solar system have interiors broadly similar to Earth's, layered, differentiated, with denser materials sinking toward the center and lighter materials rising toward the surface. Mars has a core and a mantle. Venus has a core and a mantle. Mercury, despite its small size, has a core that makes up a larger fraction of its volume than Earth's core does. The gas giants, Jupiter, Saturn, have cores of rock and ice buried beneath thousands of kilometers of hydrogen and helium, compressed to pressures that turn hydrogen metallic. The deep is the norm for planetary bodies large enough to have differentiated under their own gravity. The crust, the thin, cool, accessible layer where you live, is the anomaly, the narrow zone where pressures and temperatures happen to fall within a range that allows solid rock to remain brittle, that allows water to exist as a liquid, that allows the chemistry of life to proceed. The surface is a boundary condition, an edge case. The deep is the bulk of the planet, the default state, the region where the properties of matter are determined not by what is convenient or habitable, but by the relentless logic of physics. There is no way to make the deep accessible. No tunnel can reach it. No probe can survive the journey. The pressures and temperatures defeat any material, any design, any conceivable technology. Even if you could drill through the mantle, which you cannot, the hole would close behind you as the rock flowed back into place. Even if you could shield a probe from the heat, which you cannot, the pressure would crush it. The deep is sealed, not by choice or by secrecy, but by the fundamental constraints of matter and energy. It is not hidden. It is simply too far, too hot, too extreme, and it will remain so. There is no future technology that will change this. The barriers are not engineering problems. They are limits imposed by the nature of the materials involved and the forces acting on them. The deep is inaccessible in a permanent sense, and any knowledge of it must come from indirect methods, seismic waves, laboratory experiments, mathematical models, the occasional fragment of mantle brought to the surface by volcanic processes. These methods are sufficient. They have built a picture of the interior that is detailed and accurate, constrained by observation and tested against prediction, but they are not the same as direct experience, and they never will be. This creates a strange asymmetry. You know more about the deep than any human being who lived a century ago, and yet you are no closer to it. The knowledge has increased, but the distance has not changed. The mantle is as inaccessible now as it was when the first seismographs recorded earthquake waves passing through it. The core is as remote now as it was when its existence was first inferred. The instruments have improved, the models have become more sophisticated, the data have accumulated, but the deep itself remains exactly where it has always been, thousands of kilometers below, separated from you by barriers that are absolute. You can describe it. You can measure it. You can predict its behavior over millions of years. But you cannot go there, you cannot touch it. You cannot see it except through the lens of inference and theory. The deep exists in a realm that is knowable but not experienceable, and that distinction is fundamental. It is not a limitation of technology or ambition. It is a consequence of living on the surface of a planet large enough to have an interior that operates under conditions incompatible with human survival. And this is true not just for you, but for any life that might exist elsewhere. If there are organisms on other planets, and if those planets are large enough to be geologically active, then those organisms too will live on the surface, in the narrow zone where conditions are clement, separated from the deep by the same barriers of heat and pressure and distance. The deep is universal, in a sense. It is a feature of planets, not of Earth specifically, a consequence of size and gravity, and the way matter behaves when compressed. Wherever there are large rocky bodies, there are inaccessible interiors, regions that drive surface processes, but remain forever hidden from direct observation. The deep is not unique to this world. It is part of what it means to be a planet. There is something humbling in this, not in the sense of being made small, though you are small, but in the sense of recognizing limits. The deep is knowable, but it is not conquerable. It is not a frontier to be explored, not a wilderness to be mapped and tamed. It is simply there, operating according to its own logic, indifferent to observation, indifferent to understanding, indifferent to ambition. You can study it, and you have studied it, and the study has been fruitful, revealing structures and processes that shape the planet in profound ways. But the study does not grant access. It does not bring the deep closer. It simply makes the inaccessibility more precise, more clearly defined, more evidently absolute. The deep makes the surface possible. This is not metaphorical. Without the heat flowing from the core and mantle, without the convection currents that drive plate tectonics, the surface would be a different place. The continents would not drift. Mountains would not rise to capture moisture and create rain shadows. Ocean basins would not open and close, redistributing heat and altering currents. The carbon cycle would stall, locked in sediments with no mechanism to return carbon dioxide to the atmosphere. The planet would cool differently, not through active processes that recycle material and release gases, but through passive conduction alone, a slower, simpler cooling that would not sustain the dynamic surface conditions necessary for life as it exists on Earth. The deep is not just beneath the surface. It is the reason the surface behaves the way it does, the engine that has kept the planet geologically active for billions of years, that has maintained conditions within a range compatible with liquid water and stable climates. Plate tectonics is not inevitable. Venus, nearly the same size as Earth, and presumably built from similar materials, does not have plate tectonics. Its surface is rigid, covered by a thick crust that does not break into moving plates, and its interior heat is released through episodic volcanic resurfacing events rather than through continuous, steady recycling. Why Venus differs from Earth is not fully understood. It may be the absence of water in the Venusian mantle, which would make the rock less prone to melting and the crust less likely to fracture. It may be the surface temperature, hot enough to soften the lithosphere and prevent the kind of brittle failure that allows subduction to begin. It may be some combination of factors, some contingency in the planet's early history that set it on a different path. Whatever the reason, Venus demonstrates that plate tectonics is not a given. It is a mode of behavior that some planets exhibit and others do not, and Earth happens to be one of the planets where it occurs. This has consequences. Plate tectonics recycles the crust. It drags carbon-rich sediments into the mantle, where they are heated and release carbon dioxide that eventually returns to the atmosphere through volcanic eruptions. It builds mountain ranges that weather and draw carbon out of the atmosphere, creating a feedback loop that stabilizes climate over geological timescales. It creates diverse environments, from mid-ocean ridges to subduction zones to continental collisions, each supporting different mineral assemblages, different chemical gradients, different opportunities for the chemistry that leads to life. Life did not create plate tectonics, but plate tectonics may have made complex life possible. The early Earth had continents and oceans, but the arrangement was different, and the processes were different. Some researchers suggest that plate tectonics in its modern form began only a few billion years ago, after the planet had cooled enough for the lithosphere to become rigid and brittle, capable of breaking and sinking back into the mantle. Before that, the crust may have been too hot, too pliable, and heat may have been released through other mechanisms, through volcanic plains, through drips of dense material sinking into the mantle, through processes that left fewer traces and are harder to reconstruct. The timing is uncertain. But what is clear is that the Earth has been geologically active throughout its history, and that activity has shaped the surface in ways that are not just physical, but chemical, creating the conditions where life could arise and, once arisen, persist and diversify. The oxygen in the atmosphere came from photosynthesis, but the raw materials for photosynthesis came from volcanic outgassing and the weathering of rocks, processes driven by the deep. The nutrients that support ecosystems are cycled through erosion and sedimentation and volcanism, again driven by the deep. The deep does not sustain life directly. It sustains the systems that sustain life, the flows of material and energy that maintain the surface in a state far from equilibrium, a state where complexity can emerge and be maintained. This will not last forever. The planet is cooling, and as it cools, the forces driving plate tectonics will weaken. The mantle is losing heat, and the rate of heat loss is slow but inexorable. In a billion years, perhaps sooner, the convection currents may slow enough that plates stop moving, that subduction ceases, that the surface becomes rigid. The exact timeline is debated and depends on assumptions about the mantle's composition, the efficiency of heat transfer, and the role of water in keeping the system active. But the direction is clear. The planet is moving toward a state where the interior is no longer hot enough to drive the surface processes that have defined it for billions of years. When that happens, volcanism will decline, the carbon cycle will stall, the climate will destabilize, the magnetic field powered by the motion of the outer core will weaken and eventually cease. The planet will become geologically dead, not in the sense of being lifeless. Life might persist in isolated environments, in subsurface refuges where water and energy remain, but in the sense that the surface will no longer change, no longer be reshaped by the forces from below. This is the fate of all rocky planets. Mars reached this state early, within a billion years of its formation, because it was small and cooled quickly. The Moon, even smaller, solidified faster still, and its surface has been static for billions of years, altered only by impacts from space. Earth is larger, and its cooling is slower, but the process is the same. The deep is not eternal. It is sustained by heat, and heat dissipates. The planet is on a cooling curve, and the curve leads to quiescence, to a state where the interior is cold enough that nothing moves, nothing flows, nothing drives surface change. By the time this occurs, the sun will have evolved into a red giant, and the surface will be uninhabitable for other reasons, heated to temperatures where oceans boil and atmospheres are stripped away. The end of the deep's activity and the end of the Earth's habitability are decoupled in detail, but aligned in their inevitability. Both are consequences of the finite energy available, the finite reserves of heat stored in the interior, the relentless operation of the second law of thermodynamics. For now, the deep is active. The mantle is convecting. The core is generating the magnetic field. Plates are moving. Volcanoes are erupting. The planet is alive in the geological sense, dynamic and changing, and it will remain so for hundreds of millions or billions of years more. That is a long time by any standard that matters to life. Long enough for evolution to produce new species, for climates to shift, for continents to rearrange themselves. The deep does not care about these timelines. It operates on its own schedule, cooling at its own pace, indifferent to the biological and ecological changes occurring on the surface. But the surface depends on the deep, and the deep's eventual quieting will mark the end of an era, not just for the planet, but for any life that has adapted to the dynamic conditions the deep creates. The connection between the surface and the deep is not optional. It is structural, built into the way the planet is organized, and it has been there since the beginning. You are still standing on that thin layer. Nothing has changed. The crust is still beneath you, no thicker than it was, and beneath it the mantle continues to creep, the core continues to cool, the inner sphere continues to grow by imperceptible increments. The descent you have taken exists only as knowledge, not as movement. You have not gone anywhere. The deep remains exactly where it has always been, thousands of kilometers below, separated by distance and pressure and heat that cannot be crossed. And yet, something has shifted. Not in the planet, but in the sense of what the ground is, what it means to stand on a surface so thin that it barely registers as a presence when measured against the whole. The Earth is not the solid thing you thought it was. It is layered, dynamic, ancient beyond comprehension, and almost entirely hidden. The part you know, the part you can touch and walk on and build upon, is a vanishingly small fraction of the total. Everything else, the mantle with its slow currents, the outer core with its flowing iron, the inner core growing in darkness at the center, exists in a state you cannot witness, under conditions you cannot replicate, on timescales you cannot perceive. The deep is real, but it is real in a way that resists familiarity. It is as distant as the stars, though it lies directly beneath you, supporting every step you take. There is no conclusion to draw from this. The deep does not offer lessons. It does not teach humility or perspective or wonder, though you may feel those things when you consider it. The deep simply is. It has been there since the planet formed, and it will be there long after the surface has changed beyond recognition. It operates according to laws that do not require your understanding, that do not depend on observation or acknowledgement. The mantle will convect whether you think about it or not. The core will cool whether you measure it or not. The magnetic field will continue shielding the atmosphere, generated by forces invisible and unreachable, indifferent to gratitude or awareness. And perhaps that is enough. To know that the ground is not as solid as it seems. To know that nearly everything exists below, out of sight, inaccessible but present, patient in a way that has nothing to do with waiting. The deep does not wait. It continues. And the surface, fragile and temporary, rests upon it, shaped by it, sustained by forces that have been active for billions of years and will remain active for billions more. You stand on a film, a boundary, the thinnest imaginable crust separating the familiar from the vast. The deep is beneath you now as it has always been. It will be there when you wake tomorrow. It will be there long after you are gone. It is the permanence beneath the temporary, the hidden structure supporting everything visible, the silent engine turning in darkness, moving continents and mountains and oceans at speeds too slow to feel, but relentless enough to reshape a world. There is a kind of peace in that, not the peace of understanding because the deep cannot be fully understood, but the peace of knowing that some things continue without you, that the planet does not depend on your attention to keep functioning, that the forces shaping the world are older and larger and more patient than anything you will ever encounter in a human life. The deep asks nothing of you, it offers nothing to you, it is simply there, beneath the surface, beyond reach, doing what it has always done, and you are here, standing on a thin crust, held up by everything you cannot see. If this journey brought you a sense of calm, you can subscribe to Quiet Science and continue exploring these silent depths with us.